Photovoltaic solar panels absorb sunlight as a source of energy to generate electricity. A photovoltaic (PV) module is a packaged, connected assembly of typically 6 by 10 photovoltaic solar cells. Photovoltaic modules constitute the photovoltaic array of a photovoltaic system that generates and supplies solar electricity in commercial and residential applications. The most common application of solar energy collection outside agriculture is solar water heating systems. Theory and construction. Photovoltaic modules use light energy photons from the sun to generate electricity through the photovoltaic effect. The majority of modules use wafer-based crystalline silicon cells or thin film cells. The structural load-carrying member of a module can either be the top layer or the back layer. Cells must also be protected from mechanical damage and moisture. Most modules are rigid, but semi-flexible ones based on thin film cells are also available. The cells must be connected electrically in series, one to another. A PV junction box is attached to the back of the solar panel and it is its output interface. Externally, most of photovoltaic modules use MC4 connectors type to facilitate easy weatherproof connections to the rest of the system. Also, USB power interface can be used. Module electrical connections are made in series to achieve a desired output voltage or in parallel to provide a desired current capability amperes. The conducting wires that take the current off the modules may contain silver, copper or other non-magnetic conductive transition metals. Bypass diodes may be incorporated or used externally, in case of partial module shading, to maximize the output of module sections still illuminated. Some special solar PV modules include concentrators in which light is focused by lenses or mirrors onto smaller cells. This enables the use of cells with a high cost per unit area such as gallium arsenide in a cost-effective way. Solar panels also use metal frames consisting of racking components, brackets, reflector shapes, and troughs to better support the panel structure. History. In 1839, the ability of some materials to create an electrical charge from light exposure was first observed by Alexandre Edmond Becquerel. Though the Premiere solar panels were too inefficient for even simple electric devices, they were used as an instrument to measure light. The observation by Becquerel was not replicated again until 1873, when Willoughby Smith discovered that the charge could be caused by light hitting selenium. After this discovery, William Grills Adams and Richard Evans Day published, "The Action of Light on Selenium" in 1876, describing the experiment they used to replicate Smith's results. In 1881, Charles Fritz created the first commercial solar panel, which was reported by Fritz as continuous, constant and of considerable force not only by exposure to sunlight but also to dim, diffused daylight. However, these solar panels were very inefficient, especially compared to coal-fired power plants. In 1939, Russell Ohl created the solar cell design that is used in many modern solar panels. He patented his design in 1941. In 1954, this design was first used by Bell Labs to create the first commercially viable silicon solar cell. Efficiencies. Each module is rated by its DC output power under standard test conditions (STC), and typically ranges from 100 to 365 watts (W). The efficiency of a module determines the area of a module given the same rated output. An 8% efficient 230 W module will have twice the area of a 16% efficient 230 W module. There are a few commercially available solar modules that exceed efficiency of 24% depending on construction. Photovoltaic modules can produce electricity from a range of frequencies of light, but usually cannot cover the entire solar range, specifically ultraviolet, infrared and low or diffused light. Hence, much of the incident sunlight energy is wasted by solar modules, and they can give far higher efficiencies if illuminated with monochromatic light. Therefore, another design concept is to split the light into 6 to 8 different wavelength ranges that will produce a different color of light, and direct the beams onto different cells tuned to those ranges. This has been projected to be capable of raising efficiency by 50%. A single solar module can produce only a limited amount of power. Most installations contain multiple modules. A photovoltaic system typically includes an array of photovoltaic modules, an inverter, a battery pack for storage, interconnection wiring, and optionally a solar tracking mechanism. Scientists from Spectrolab, a subsidiary of Boeing, have reported development of multi-junction solar cells with an efficiency of more than 40%, a new world record for solar photovoltaic cells. The Spectrolab scientists also predict that concentrator solar cells could achieve efficiencies of more than 45% or even 50% in the future, with theoretical efficiencies being about 58% in cells with more than 3 junctions. Currently, the best achieved sunlight conversion rate solar module efficiency is around 21.5% in new commercial products, typically lower than the efficiencies of their cells in isolation. The most efficient mass-produced solar modules have power density values of up to 175 with M2, 16.22 with feet 2. Research by Imperial College, London has shown that the efficiency of a solar panel can be improved by studding the light-receiving semiconductor surface with aluminum nanocylinders similar to the ridges on Lego blocks. The scattered light then travels along a longer path in the semiconductor, which means that more photons can be absorbed and converted into current. Although these nanocylinders have been used previously, aluminum was preceded by gold and silver, the light scattering occurred in the near-infrared region and visible light was absorbed strongly. Aluminum was found to have absorbed the ultraviolet part of the spectrum, while the visible and near-infrared parts of the spectrum were found to be scattered by the aluminum surface. This, the research argued, could bring down the cost significantly and improve the efficiency, as aluminum is more abundant and less costly than gold and silver. The research also noted that the increase in current makes thinner film solar panels technically feasible without compromising power conversion efficiencies, thus reducing material consumption. Efficiencies of solar panel can be calculated by MPP, maximum power point value of solar panels. Solar inverters convert the DC power to AC power by performing MPPT process. Solar inverter samples the output power IV curve from the solar cell and applies the proper resistance load to solar cells to obtain maximum power. MPP maximum power point of the solar panel consists of MPP voltage VMPP and MPP current IMPP. It is a capacity of the solar panel, and the higher value can make higher MPP. Micro-inverted solar panels are wired in parallel, which produces more output than normal panels which are wired in series, with the output of the series determined by the lowest performing panel. This is known as the Christmas light effect. Microinverters work independently, so each panel contributes its maximum possible output given the available sunlight. Topic: Technology. Most solar modules are currently produced from crystalline silicon (CC) solar cells made of multicrystalline and monocrystalline silicon. In 2013, crystalline silicon accounted for more than 90% of worldwide PV production, while the rest of the overall market is made up of thin film technologies using cadmium telluride, SiGs and amorphous silicon. Emerging, third-generation solar technologies use advanced thin film cells. They produce a relatively high efficiency conversion for the low cost compared to other solar technologies. Also, high cost, high efficiency, and close-packed rectangular multi-junction (MJ) cells are preferably used in solar panels on spacecraft, as they offer the highest ratio of generated power per kilogram lifted into space. MJ cells are compound semiconductors and made of gallium arsenide, gallium-3 arsenide, and other semiconductor materials. Another emerging PV technology using MJ cells is concentrator photovoltaics (CPV). Topic: Thin film. In rigid thin film modules, the cell and the module are manufactured in the same production line. The cell is created on a glass substrate or superstrate, and the electrical connections are created in situ, a so-called monolithic integration. The substrate or superstrate is laminated with an encapsulant to a front or back sheet, usually another sheet of glass. The main cell technologies in this category are cadmium telluride, or a C, or a C plus UCC tandem, or CIGS or variant. Amorphous silicon has a sunlight conversion rate of 6 to 12%. Flexible thin film cells and modules are created on the same production line by depositing the photoactive layer and other necessary layers on a flexible substrate. If the substrate is an insulator, e.g. polyester or polyamide film, then monolithic integration can be used. If it is a conductor, then another technique for electrical connection must be used. The cells are assembled into modules by laminating them to a transparent colorless fluoropolymer on the front side, typically ETFE or FEP, and a polymer suitable for bonding to the final substrate on the other side. Topic: Smart solar modules. Several companies have begun embedding electronics into PV modules. This enables performing maximum power point tracking (MPPT) for each module individually, and the measurement of performance data for monitoring and fault detection at module level. Some of these solutions make use of power optimizers, a DC to DC converter technology developed to maximize the power harvest from solar photovoltaic systems. As of about 2010, such electronics can also compensate for shading effects, wherein a shadow falling across a section of a module causes the electrical output of one or more strings of cells in the module to fall to zero, but not having the output of the entire module fall to zero. Topic: Performance and degradation. Module performance is generally rated under standard test conditions (STC), irradiance of 1000 with M2, solar spectrum of AM 1.5 and module temperature at 25 degrees Celsius. Electrical characteristics include nominal power (PMAX), measured in W, open circuit voltage (VOC), short circuit current (ISC), measured in amperes, maximum power voltage (VMPP), maximum power current (IMPP), peak power (watt peak, WP), and module efficiency %. Nominal voltage refers to the voltage of the battery that the module is best suited to charge. This is a leftover term from the days when solar modules were only used to charge batteries. The actual voltage output of the module changes as lighting, temperature and load conditions change, so there is never one specific voltage at which the module operates. Nominal voltage allows users, at a glance, to make sure the module is compatible with a given system. Open circuit voltage or VOC is the maximum voltage that the module can produce when not connected to an electrical circuit or system. VOC can be measured with a voltmeter directly on an illuminated module's terminals or on its disconnected cable. The peak power rating, WP, is the maximum output under standard test conditions, not the maximum possible output. Typical modules, which could measure approximately 1 meter times 2 meters or 3 feet 3 in times 6 feet 7 in, will be rated from as low as 75 W to as high as 350 W, depending on their efficiency. At the time of testing, the test modules are binned according to their test results, and a typical manufacturer might rate their modules in 5W increments, and either rate them at plus or minus 3%, plus or minus 5%, plus 3, minus 0% or plus 5, minus 0%. The ability of solar modules to withstand damage by rain, hail, heavy snow load, and cycles of heat and cold varies by manufacturer, although most solar panels on the U.S. market are ALLAH listed, meaning they have gone through testing to withstand hail. Many crystalline silicon module manufacturers offer a limited warranty that guarantees electrical production for 10 years at 90% of rated power output and 25 years at 80%. Potential induced degradation, also called PID, is a potential induced performance degradation in crystalline photovoltaic modules, caused by so-called stray currents. This effect may cause power loss of up to 30%. The largest challenge for photovoltaic technology is said to be the purchase price per watt of electricity produced. New materials and manufacturing techniques continue to improve the price to power performance. The problem resides in the enormous activation energy that must be overcome for a photon to excite an electron for harvesting purposes. Advancements in photovoltaic technologies have brought about the process of doping the silicon substrate to lower the activation energy, thereby making the panel more efficient in converting photons to retrievable electrons. Chemicals such as boron P-type are applied into the semiconductor crystal in order to create donor and acceptor energy levels substantially closer to the valence and conductor bands. In doing so, the addition of boron impurity allows the activation energy to decrease 20-fold from 1.12 electron volts to 0.05 electron volts. Since the potential difference EB is so low, the boron is able to thermally ionize at room temperatures. This allows for free energy carriers in the conduction and valence bands, thereby allowing greater conversion of photons to electrons. Maintenance. Solar panel conversion efficiency, typically in the 20% range, is reduced by dust, grime, pollen, and other particulates that accumulate on the solar panel. A dirty solar panel can reduce its power capabilities by up to 30% in high dust, pollen or desert areas, says Seamus Curran, Associate Professor of Physics at the University of Houston and Director of the Institute for Nanoenergy, which specializes in the design, engineering, and assembly of nanostructures. Paying to have solar panels cleaned is often not a good investment. Researchers found panels that had not been cleaned, or rained on, for 145 days during a summer drought in California, lost only 7.4% of their efficiency. Overall, for a typical residential solar system of 5 kilowatts, washing panels halfway through the summer would translate into a mere $20 gain in electricity production until the summer drought ends—in about 2.5 months. For larger commercial rooftop systems, the financial losses are bigger but still rarely enough to warrant the cost of washing the panels. On average, panels lost a little less than 0.05% of their overall efficiency per day. Recycling. Most parts of a solar module can be recycled, including up to 95% of certain semiconductor materials or the glass, as well as large amounts of ferrous and non-ferrous metals. Some private companies and non-profit organizations are currently engaged in take-back and recycling operations for end-of-life modules. Recycling possibilities depend on the kind of technology used in the modules. Silicon-based modules, aluminum frames and junction boxes are dismantled manually at the beginning of the process. The module is then crushed in a mill and the different fractions are separated: glass, plastics and metals. It is possible to recover more than 80% of the incoming weight. This process can be performed by flat glass recyclers, since morphology and composition of a PV module is similar to those flat glasses used in the building and automotive industry. The recovered glass, for example, is readily accepted by the glass foam and glass insulation industry. non-silicon-based modules, they require specific recycling technologies such as the use of chemical baths in order to separate the different semiconductor materials. For cadmium telluride modules, the recycling process begins by crushing the module and subsequently separating the different fractions. This recycling process is designed to recover up to 90% of the glass and 95% of the semiconductor materials contained. Some commercial-scale recycling facilities have been created in recent years by private companies. For aluminium flat-plate reflector, the trendiness of the reflectors has been brought up by fabricating them using a thin layer around 0.016 mm to 0.024 mm of aluminum coating present inside the non-recycled plastic food packages. Since 2010, there is an annual European conference bringing together manufacturers, recyclers and researchers to look at the future of PV module recycling. Production. In 2010, 15.9 gigawatts of solar PV system installations were completed, with solar PV pricing survey and market research company PV Insights reporting growth of 117.8% in solar PV installation on a year-on-year basis. With over 100% year-on-year growth in PV system installation, PV module makers dramatically increased their shipments of solar modules in 2010. They actively expanded their capacity and turned themselves into gigawatt GW players. According to PV Insights, 5 of the top 10 PV module companies in 2010 are GW players. Suntech, First Solar, Sharp, Yingli and Trina Solar are GW producers now, and most of them doubled their shipments in 2010. The basis of producing solar panels revolves around the use of silicon cells. These silicon cells are typically 10 to 20% efficient at converting sunlight into electricity, with newer production models now exceeding 22%. In order for solar panels to become more efficient, researchers across the world have been trying to develop new technologies to make solar panels more effective at turning sunlight into energy. In 2014, the world's top 4 solar module producers in terms of shipped capacity during the calendar year of 2014 were Yingli, Trina Solar, Sharp Solar and Canadian Solar. Topic: Price. The price of solar electrical power has continued to fall so that in many countries it has become cheaper than ordinary fossil fuel electricity from the electricity grid since 2012, a phenomenon known as grid parity. Average pricing information divides in 3 pricing categories: those buying small quantities, modules of all sizes in the kilowatt range annually, mid-range buyers, typically up to 10 MWP annually, and large quantity buyers, self-explanatory, and with access to the lowest prices. Over the long term there is clearly a systematic reduction in the price of cells and modules. For example, in 2012 it was estimated that the quantity cost per watt was about 60 cents, which was 250 times lower than the cost in 1970 of $150. A 2015 study shows price per kilowatt-hour dropping by 10% per year since 1980, and predicts that solar could contribute 20% of total electricity consumption by 2030, whereas the International Energy Agency predicts 16% by 2050. Real-world energy production costs depend a great deal on local weather conditions. In a cloudy country such as the United Kingdom, the cost per produced kWh is higher than in sunnier countries like Spain. According to S. Energy Information Administration, prices per megawatt-hour are expected to converge and reach parity with conventional energy production sources during the period 2020 to 2030. According to EIA, the parity can be achieved without need for subsidy support and can be accomplished through organic market mechanisms, namely production price reduction and technological advancement. Following to RMI, balance of system (BOS) elements, this is, non-module cost of non-microinverter solar modules as wiring, converters, racking systems and various components make up about half of the total costs of installations. For merchant solar power stations, where the electricity is being sold into the electricity transmission network, the cost of solar energy will need to match the wholesale electricity price. This point is sometimes called wholesale grid parity or busbar parity. Some photovoltaic systems, such as rooftop installations, can supply power directly to an electricity user. In these cases, the installation can be competitive when the output cost matches the price at which the user pays for his electricity consumption. This situation is sometimes called retail grid parity, socket parity, or dynamic grid parity. Research carried out by UN Energy in 2012 suggests areas of sunny countries with high electricity prices, such as Italy, Spain and Australia, and areas using diesel generators, have reached retail grid parity. Mounting and tracking. Ground-mounted photovoltaic systems are usually large, utility-scale solar power plants. Their solar modules are held in place by racks or frames that are attached to ground-based mounting supports. Ground-based mounting supports include pole mounts, which are driven directly into the ground or embedded in concrete. Foundation mounts, such as concrete slabs or poured footings. Ballasted footing mounts, such as concrete or steel bases that use weight to secure the solar module system in position and do not require ground penetration. This type of mounting system is well suited for sites where excavation is not possible, such as capped landfills, and simplifies decommissioning or relocation of solar module systems. Roof-mounted solar power systems consist of solar modules held in place by racks or frames attached to roof-based mounting supports. Roof-based mounting supports include rail mounts, which are attached directly to the roof structure and may use additional rails for attaching the module racking or frames. Ballasted footing mounts, such as concrete or steel bases that use weight to secure the panel system in position and do not require through penetration. This mounting method allows for decommissioning or relocation of solar panel systems with no adverse effect on the roof structure. All wiring connecting adjacent solar modules to the energy harvesting equipment must be installed according to local electrical codes and should be run in a conduit appropriate for the climate condition. Solar trackers increase the amount of energy produced per module at a cost of mechanical complexity and need for maintenance. They sense the direction of the sun and tilt or rotate the modules as needed for maximum exposure to the light. Alternatively, fixed racks hold modules stationary as the sun moves across the sky. The fixed rack sets the angle at which the module is held. Tilt angles equivalent to an installation's latitude are common. Most of these fixed racks are set on poles above ground. Panels that face west or east may provide slightly lower energy, but evens out the supply, and may provide more power during peak demand. Standards. Standards generally used in photovoltaic modules: IEC 61215 crystalline silicon performance, 61646 thin film performance, and 61730 all modules, safety. ISO 9488 solar energy. Vocabulary: UL 1703 from Underwriters Laboratories, UL 1741 from Underwriters Laboratories, UL 2703 from Underwriters Laboratories, CE mark. Electrical Safety Tester EST Series EST 460, EST22V, EST22H, EST 110. Connectors. Outdoor solar panels usually includes MC4 connectors. Automotive solar panels also can include car lighter and USB adapter. Indoor panels including solar PV glasses, thin films and windows can integrate microinverter AC solar panels. Topic: Applications. There are many practical applications for the use of solar panels or photovoltaics. It can first be used in agriculture as a power source for irrigation. In healthcare, solar panels can be used to refrigerate medical supplies. It can also be used for infrastructure. PV modules are used in photovoltaic systems and include a large variety of electric devices. Photovoltaic power stations, rooftop solar PV systems, standalone PV systems, solar hybrid power systems, concentrated photovoltaics, solar planes, solar pumped lasers, solar vehicles, solar panels on spacecrafts and space stations. Topic: Limitations. Topic: Pollution and energy in production. Solar panel has been a well-known method of generating clean, emission-free electricity. However, it produces only direct current electricity (DC), which is not what normal appliances use. Solar photovoltaic systems, solar PV systems are often made of solar PV panels, modules, and inverter, changing DC to AC. Solar PV panels are mainly made of solar photovoltaic cells, which has no fundamental difference to the material for making computer chips. The process of producing solar PV cells, computer chips, is energy intensive and involves highly poisonous and environmental toxic chemicals. There are few solar PV manufacturing plants around the world producing PV modules with energy produced from PV. This measure greatly reduces the carbon footprint during the manufacturing process. Managing the chemicals used in the manufacturing process is subject to the factory's local laws and regulations. Topic: Impact on electricity network. With the increasing levels of rooftop photovoltaic systems, the energy flow becomes two-way. When there is more local generation than consumption, electricity is exported to the grid. However, electricity network traditionally is not designed to deal with the two-way energy transfer. Therefore, some technical issues may occur. For example, in Queensland, Australia, there have been more than 30% of households with rooftop PV by the end of 2017. The famous Californian 2020 duck curve appears very often for a lot of communities from 2015 onwards. An over-voltage issue may come out as the electricity flows from these PV households back to the network. There are solutions to manage the over-voltage issue, such as regulating PV inverter power factor, new voltage and energy control equipment at electricity distributor level, reconducting the electricity wires, demand-side management, etc. There are often limitations and costs related to these solutions. Topic: Implication onto electricity bill management and energy investment. There is no silver bullet in electricity or energy demand and bill management, because customers sites have different specific situations, e.g. different comfort, convenience needs, different electricity tariffs, or different usage patterns. Electricity tariff may have a few elements, such as daily access and metering charge, energy charge based on kWh, MWh, or peak demand charge, e.g. a price for the highest 30 minutes energy consumption in a month. PV is a promising option for reducing energy charge when electricity price is reasonably high and continuously increasing, such as in Australia and Germany. However, for sites with peak demand charge in place, PV may be less attractive if peak demands mostly occur in the late afternoon to early evening, for example residential communities. Overall, energy investment is largely an economical decision, and it is better to make investment decisions based on systematical evaluation of options in operational improvement, energy efficiency, on-site generation and energy storage.